this lesson, we're going to talk about calorimetry and how we use it to calculate heat transfer between objects. Let's look at an example here. We have the same substance, the same mass. What happens to these two objects if the temperature of A is greater than the temperature of B? Note that we're only going to see the flow of heat. We never see the flow of cold. What do you think is going to happen when we have one hot object and one cold object? We're going to see the flow of heat from A to B. A is hotter, B is colder. We put them in contact with one another, and heat is going to flow from the hotter object to the colder object. This is the same thing that happens when we look at ice in a cup of water. The water is warmer than the ice. Heat flows from the water to the ice and causes the ice to melt. Thermal equilibrium occurs when objects which are in contact with one another transfer heat until they are at the same temperature as each other. Note that that temperature, while it will be between the two original temperatures, will not be necessarily halfway between those two temperatures. If we have a block of tin at 50 degrees and a block of brass at 20 degrees, there is going to be the transfer, but these substances have different specific heat values. And as a result, the way one loses heat and the rate at one gains heat is going to be a little bit different. When these two objects are placed in contact with one another, they will get to thermal equilibrium, and at that point, the temperature of the tin will equal the temperature of the brass. If we have a block of tin at 50 degrees, a block of brass at 20 degrees Celsius, which way will the heat flow? And the heat flows from the tin to the brass because it's at a higher temperature. When these two objects reach thermal equilibrium, they will be at 31 degrees Celsius. Remember, we started at 50 and 20. We're not necessarily going to go to the halfway point. They don't meet in the middle of those two temperatures because the specific heat of these two substances is different. Calorimetry is used to measure the energy change associated with the change in a system. And what we'll see are these Q terms, and the number of Q values depends on the number of things or substances in a system. For example, if there were 3 objects, we'd have 3 Q values. If there were 8 objects, we'd have 8 Q values. We can use calorimetry to quantify the heat transfer between two objects. For example, we can identify what the final temperature is for the two objects once they reach thermal equilibrium. In this case, we're defining our system as the water plus the metal. That's the only thing we're worried about. Remember, we define our system. And we're also going to assume that no heat is lost to the surroundings. Now, in reality, heat is lost to the surroundings. However, to simplify the calculations, we're going to assume that no heat is lost to the surroundings. And that's typically what we will be able to do when we're solving calorimetry problems in this course. In this case, we have a metal sphere in the beaker with water. So we have Q metal, which is the heat of the metal, plus Q of the water. And we know that the sum of those must add up to 0 because we've already said that heat is not lost to the surroundings. We can rearrange that to see that Q of metal equals minus Q of water. And when you're doing these problems, be careful about your negative signs. One of the easiest mistakes to make in these problems is losing a negative sign. And I say that because I am one of those people that easily loses negative signs when I'm solving problems. So I know that about me, and I have to take extra care when I'm doing problems that have negatives in them. Let's look at an example. A 25-gram block of lead, 0.129 joules per gram degree Celsius for its specific heat, initially at 45 degrees Celsius, is placed in contact with a 15-gram block of aluminum, 0.897 joules per gram degree Celsius, initially at 12.5 degrees Celsius. What is the final temperature of each block? Assume no heat is lost to the surroundings. The first thing I want to do is picture what's going on. So I have two objects which are placed in contact with one another, and we've just distinguished these by making them different colors. Let's look at what we know about the lead, and we'll mark that for the red block. It's 25 grams, 0.129 joules per gram degree Celsius, and the initial temperature is 45 degrees. That was all given in the problem. Now we can look at the aluminum, which we've indicated in green here. It's 15 grams, 0.897 joules per gram degree Celsius, and has an initial temperature of 12.5 degrees Celsius. Now we need to start setting up our problem so that we can solve for that final temperature. because that's what we're trying to find. And we know that the final temperature for both of those objects is going to be the same because they're going to get to thermal equilibrium and they will get to the same value. We can set up an equation. Q of lead plus Q of aluminum equals 0 because we're making the assumption that all heat is transferred from one object to another in our system. And each Q value can be calculated by using the equation MCS delta T, which we've used previously. Now we need to set it up with the values that we were given in the problem. So we have 25 grams of the lead, which has a specific heat of 0.129 joules per gram degree Celsius. Multiply that by delta T, remember T final minus T initial, always final minus initial, plus the same thing for our aluminum block, which is 15 grams times 0.897 joules per gram degree Celsius, TF minus 12.5 degrees Celsius. And those add up to 0. At this point, we're really just dealing with an algebra problem. Now we need to solve for TF. The first thing I'm going to do is multiply my 25 by 0.129 and get 3.225 times TF minus 45 plus 13.455 times TF minus 12.5, and that equals 0. Now I need to carry those numbers through the parentheses. We get 3.225 TF minus 145.125 plus 13.455 TF minus 168.188. Again, still equal to 0. Now I can combine my terms with TF to get 16.68 TF minus 313.313 and set that equal to 0. I move the 313 to the other side, and then I divide by the 16.68, and we get that the final temperature is 18.8 degrees Celsius. And this answer is a reasonable answer. What we see is that we have one object start at 45, the other start at 12.5. The final temperature had to be somewhere between those two values. It could never be greater than 45 or less than 12.5 because we made the assumption that no heat was lost to the surroundings. The previous example looked at dealing with heat transferring between two objects, but we also need to look at what happens when there's a chemical reaction that occurs. And there are two types of calorimetry that we can do in a lab to measure the heat change for an actual chemical reaction. One of these is a constant volume calorimeter, and in this one we have a sealed metal container so that the volume inside the system is exactly the same. We have a water bath around our sample vessel. We have the reaction that occurs, and then we also can measure the heat absorbed by the calorimeter, and we can add those up to get 0. This is an experiment we do in an upper level class, not something we typically do in a first year chemistry class. However, we can also do what's called constant pressure calorimetry. In this case, it's open to the atmosphere, and that's so the pressure is constant. And we do this very low tech. We have two nested styrofoam coffee cups together, a cardboard cover, and we can do the reaction, measure the temperature change of the water, and then figure out what the energy associated with that reaction is. Let's look at an example for a constant pressure calorimetry problem. When a student mixes 50 milliliters of 1.00 molar HCl and 50 milliliters of 1.00 molar NaOH in a coffee cup calorimeter, the temperature of the resultant solution increases from 21 degrees Celsius to 27.5 degrees Celsius. Calculate the Q of the reaction, assuming the calorimeter absorbs a negligible amount of heat, that the total volume of the solution is 100 milliliters, that its density is 1 gram per milliliter, and that its specific heat is 4.18 joules per gram degree Celsius. Note when we're dealing with dilute aqueous solutions, we can use the density and specific heat for water. Another thing we need to pay attention to is that it says the calorimeter absorbs a negligible amount of heat. And what that lets us do is simplify the Q-cal term to 0. The first thing we look at is Q of reaction, which is the heat resulting from the actual chemical reaction that occurs between the HCl and the NaOH. Next, we have the Q of solution. This is the heat absorbed by the solution that was produced by the chemical reaction. And we've already established that the Q of calorimeter is going to be 0 because it's negligible amount of heat absorbed by the calorimeter. Which one of these is true? Remember, we had Q of reaction plus Q of solution equals 0. We can rearrange that to get Q of reaction equals minus Q of solution. So B is the correct answer. We're looking at the same problem, but now we want to calculate Q of solution in kilojoules. Q equals MCS delta T. We know that we have 100 grams of water because we had 100 milliliters. The density is 1 gram per milliliter. So we have 100 grams of solution. We use our specific heat, 4.18 joules per gram degree Celsius. And we know the final and initial temperature, so we can calculate delta T. Grams cancel, Celsius cancels, and we're left with units of joules. Q equals 2,717 joules. So Q equals 2.72 kilojoules. And this is the Q of solution. This is the amount of heat absorbed by the solution as a result of the chemical reaction that occurred between HCl and NaOH. Now we need to find Q of reaction. Remember that Q of reaction equals minus Q of solution. We already established that earlier. If I know Q of solution, I can find Q of reaction because it's just the negative of that value. And that worked in this case because we were able to assume that the calorimeter absorbed a negligible amount of heat, so we only had the two Q terms added together, which equaled 0.